Yeah. Yeah.
Εσύ είσαι τώρα εδώ, στο room 1.
Ναι.
Okay.
Σας.
Γεια σου, Θανάση. Φεύγω εγώ τώρα από εδώ. Προφανώς.
Ο Διονύσης κάνει το...
Όχι, ακόμα δεν είμαι. Νομίζω ότι εγώ είμαι στο...
Όχι εσύ. Ο Διονύσης, λέω, σε αυτό το session.
Ο Διονύσης είναι, εγώ φεύγω, αυτό σας λέω. Εγώ σας ακούω, σβήνω και...
Σάκη, εσείς είστε η chair, εγώ απλά σας προσφωνίζω.
Είμαι εγώ. Εμείς θα κάνουμε handling δηλαδή.
Ναι.
Άρα τι κάνουμε? Πρώτα κάνουμε τις παρουσιάσεις που έχουμε, ένα 10 λεπτό καθής. Μετά ένα 5 λεπτά είναι τα παιδιά που έχουμε στο πρόγραμμα.
Ναι, ακριβώς.
Εντάξει. Είναι και... Hi, it's Dr. Daisuke Nohara.
Hello, Professor Lucas.
Hi.
Yeah, how are you?
I'm Sakis Lucas.
So how do we organize the session? I mean,
I will make an introduction. I will present you, and then you will take the floor, and you are going to start with your presentations. And
okay.
You will start with your presentation, Daisuke, and I'll follow, and then we'll handle the presentations of the youngsters.
Okay. Good.
We're going to start in about 1 minute.
Yeah. Are you in Japan now, Daisuke?
Yeah, I'm in Japan.
What time is now?
It's 8 p.m.
8 p.m.
Yeah,
Yes.
8 p.m. in Japan.
It's 2 p.m.
2 p.m. Yeah.
6 hours difference. Time difference.
It was 7 hours difference until the last Sunday of March. And actually forgot that it. So yesterday I missed the first session of the technical test. And I realized I was wrong.
Okay, shall we start?
Yes.
Yes.
So, good morning or good evening to everyone, depending on what time zone you are, and welcome to this first session of the Online Water Youth Congress. The thematic of this session is water-related disasters and climate crisis, and let me introduce the two mentors who will then chair this session. First of all, it is our pleasure to have Professor Athanasios Loukas, who is currently an Associate Professor of Hydrology and Water Resources in the School of Rural and Serving Engineering in Aristotle University of Thessaloniki. He is the Director of the Master Program Water Resources, and he is also Editor-in-Chief of the EWRA European Water Journal, and also Section Editor-in-Chief of the MDPI Water Journal. Our second mentor is Dr. Daisuke Nohara, who is Senior Researcher at Kajima Technical Research Institute of Japan and has a background on water resources engineering and operational hydrology. So, Professor Loukas and Dr. Nohara, the floor is yours. I think that Dr. Nohara will start with his presentation.
Okay.
Thank you.
Okay, so thank you very much for joining this session. Good morning, good afternoon, and good evening to its young delegates from all over the world. So it's my pleasure to share my talk in this Congress. So today, to kick off this session, I'd like to share some information about adaptation technologies to climate change recently studied. Integrated reservoir operation for sustainable water resources management and the changing climate. So, as you know well, this concerns that climate change further intensified the extreme rainfall, and it is actually occurring in Japan in recent years. So, in 2019, we had record floods induced by Typhoon Hagibis, which is a super typhoon in eastern Japan, killing more than 100 people in this region. And 1 year before, we also had record floods in the western Japan, and this time due to very active seasonal front rain system, killing more than 200 people, including the casualties due to landslides. And we also had another record floods in the Kuma River basin, the south part of Japan in 2020. This time killed more than 60 people. So like this way, we have suffered from extreme flood events almost every year recently in Japan, while we are still suffered from severe droughts once in several years or 10 years. So recent studies revealed that climate change or global warming contributed to intensify these extreme heavy rainfall event. So the total rainfall amount in the Western Japan floods occurred in 2018 was increased by 6 to 7% due to historical warming since 1980. And another study also showed that the rainfall amount was increased by almost 11% in floods in the eastern Japan induced by Typhoon Hagibis 2019. So these are almost corresponding to the theoretical relationships between humidity increase and temperature increase called Clausius-Clapeyron relations, which is saying that humidity increases by 7% with every increase 1 degree Celsius increase in temperature. And actually, air temperature in Japan have increased by 0.8 Kelvin since 40 years ago up to now. So anyway, many river basins received extreme rainfall beyond the designed level of river planning already. So, and this will be further intensified under the future climate. So how do we cope with these intensified flood disasters? So as a countermeasures to such intensified flood disasters, integrated reservoir operations considering advanced hydrological prediction being studied. And especially in Japan, we are now focusing on the potential effectiveness of prior release operation of the reservoirs, considering real-time hydrological prediction for enhancement of flood management. So in this operation, the reservoirs keeps their water level as high as possible in non-flood condition, at the same time as safely decreasing water level in advance, just in advance of flood events, so that the reservoir can secure the enlarged storage capacity for flood control for extreme flood events, while securing water recovery after the flood event for long-term water use operation. And now we also have long-range operational and some hydrological forecasts. And some of them have a real time of more than 1 week, and some of them more than 2 weeks. And they provide multiple possible prediction scenarios, which contributes to better and certainly handling robust decision making, both of which are very important for reservoir operation considering real-time hydrological prediction. So we are now trying to develop a prior release operation method considering this long range and some rainfall forecast. So this method provides the reservoirs to start prior release operation from long days before flood occurs to secure and large empty volume in the reservoir by gradual drawdown. This is for flood management. And also this method can provide information on a recoverable amount for drawdown from the reservoir with a high probability by focusing on the ensemble members with smaller prediction of accumulated inflow. This is for water supply. And also, if we conduct prior release operation by using the outlet for hydropower, so we can generate hydropower at the same time of prior release operation. So it's not we just waste the water stored in the reservoir only for the flood management, but we can produce energy as a low carbon energy during the prior release operation, which is also contribute to the mitigation of climate change impact. So this is an example of the effects of the prior release operation for flood management. So as you can see in the bottom figure, with prior release operation, the reservoir could mitigate or decrease its sewage volume gradually, almost 6 days before the flood occurrence. And then we can, the reservoir could secure the enlarged empty volume for flood control before the extreme flood event. And thanks to that, the maximum release rate during the flood control was mitigated by 10%, while securing water recovery after the flood event. On the other hand, according to the recent studies on assessment of climate change impact of reservoir operation for water use purposes, the average sewage volume may be decreased and in the future climate condition because of the increased evapotranspiration due to the warmer climate, as well as hydrological changes such as shifts in the river flow peak due to the changes in processes of snowfall or snow melt. So actually, under the future climate conditions, the required storage capacity for water supply will be increased according to the studies. And as you can see in the right figures, so required storage capacity for the water supply or drought management at the designed level will be greater than the total effective storage capacity of existing reservoirs. So this means existing reservoirs can no longer perfectly manage the drought with the designed level. So we need to require additional storage volume. But it is actually very difficult to construct new reservoirs because of the social conditions or environmental issues or a shortage of the good site for construction of reservoirs. So we need to consider to enhance the operation of existing reservoirs for drought management. So one possibility is dam upgrading or physical enhancement of the reservoirs or water demand reduction, as well as integrated operation of the reservoir. So I just focus on dam upgrading here. So actually this dam upgrading projects have been implemented in many places in Japan in order to increase the capability of reservoirs. So this dam upgrading includes raising dam body so that the reservoir can have enlarged storage capacity, as well as installation of additional spillways or flood spillway channels so that the reservoir can have increased capability for flood control. So lastly, as future steps, incorporating water quality aspects such as sediment management is also very important for the reservoir management and the river basin management. So this will be the next step for more integrated reservoir operation for sustainability of reservoirs downstream river environment. And as concluding remarks of my presentation, integrated reservoir operation is a key technique for adaptation to climate change by improving the water, food, energy, environment nexus. So the studies in this field is very important also from now on. Okay, thank you very much.
Okay. Do I have to start, Dionysis?
Yes, of course.
Okay. Hi, everybody. Thank you very much to the organizers for inviting me in this conference, online youth conference about water and the impacts of climate change. I will share my screen. Can you see my screen?
Yes. Fine.
Just a moment, something happened. So I'm trying to
It's not on the full screen mode.
yeah, I'm trying to put the full screen, but it seems it doesn't work. I'm sorry. Now it will work, I hope. Okay, my presentation, the title of my presentation is Climate Change Impact on Hydrometeorological Hazards, and we'll make a specific reference to agricultural water use, and will focus in the Mediterranean basin. So we know that in the UNESCO for the Sustainable Development Goals, water is one of the main goals, and in this left-hand side picture, we can see how water is in very close relation with other goals as well. And on the right-hand side, we can see how COVID has affected the water use.
Professor, I'm sorry, we are not seeing, but the first slide. It's not on the full screen mode.
Sorry, I'll do that again. What is wrong? Now you can see?
No.
No.
We can see your presentation, but not on
It doesn't move, huh?
Yes. If you have a problem, you can move it manually from slide to slide.
Hello, Professor Loukas. I'm Nicholas from the IT department. Could you please use on the right-hand side the book view of the presentation? This will help you.
Yes, this is what I...
No, the next one, not this one.
This one. Now it works,
No.
is it?
Have you closed the view, the previous view?
Can you see my screen now?
What we see is climate change variability and uncertainty. The third slide.
Yes, slide. Okay, if it doesn't work, I do with the book view again.
This
Okay.
is the correct.
This is the correct. Does it move?
Yes, it does move.
Okay, thank you. So we assess climate change with large climate models, global climate models, as well as for various socioeconomic scenarios. SRES 2 years ago with RCP's representative consideration pathways, and we can see for the various scenarios that we have different projections of the CO2 equivalent consideration in the atmosphere. And we can see the very large variability. And actually, if we use a number of, because there are many climate models, global circulation models, for the various scenarios, you can see a very large spread. If we want to synthesize this, we can say that there is a very large uncertainty which is increasing as we're going towards the end of the century. And the major sources of uncertainty are the internal variability of the system, the modeling system, climate model uncertainty, and emissions scenarios uncertainty. With the scenario uncertainty and the model spread being the larger sources of uncertainty. Let's go to see what happened on some key parameters, the impacts of climate change on precipitation. Here we can see how the precipitation is going to change as we're going towards the end of the century in Europe. And as we may see that the impact will be much larger for summer precipitation, and we'll have much more drier periods in the Mediterranean area. Now for the drought duration severity, this is a two-dimensional, these are two-dimensional graphs for 4 RCPs by Wanders and his associates. And we can see that we expect to have severe droughts with longer drought duration are the red areas marked in this global map, and we can see also that the Mediterranean area is one of these hotspot areas. And now if we look into the renewable water resources, this is from publication by Dew and his associates, very recent, I think is this paper is published last October. And again, for 3 scenarios, we can see that we have areas in the world where we'll have increase of the renewable water resources, but areas also that we have less renewable water resources, and one of these areas is the Mediterranean basin. Now, in the title I wrote that we'll look into the agricultural water use. Why? Because for the majority of the areas in the world, agriculture is the main consumer of water. And why the Mediterranean basin, as I said before, is one of the hot spots for climate change. The climatic zones in the Mediterranean basin are quite variable. Agriculture is the major economic activity and the most vulnerable activity. And of course, agriculture is also, as we can see from the graphs below, that is the main water consumer, especially in the southern part of the Mediterranean basin. So what I did is that I did a review analysis with papers published the last 6 years from 2015 to 2021. These papers used various models, GCMs, RCMs, and statistical downscaling methods to downscale the results, using also various emission scenarios. And we said that the mid of the century is around 2050, and the end of the century period is close to the end of the century, of course, 2100. So from the analysis of these papers and also our papers focusing mainly in Greece and in the Eastern Mediterranean area, we found that the annual precipitation will decrease by 10 to 30% by 2100, but we'll have inconsistent results for the mid-century period. Larger decrease is expected in summer precipitation than in winter precipitation, and the mean annual temperature will have a gradual decrease up to 2 to 3 degrees Celsius by the end of the century. Now, the impacts on storms and extreme rainfall is that first of all, the convective activity in the atmosphere will increase, producing larger atmospheric instability. However, the annual maximum rainfall will decrease by 3 to 10%. The winter maximum rainfall decreases or will remain unchanged, although the summer maximum rainfall will increase. And the results show a very large variability over the Mediterranean basin, especially in central and northern, larger than in central and northern Europe. Now for the droughts, we're expecting to have increased frequency, severity, and duration of droughts. Drought frequency will increase by 4 events per year. We'll have more dry days, larger by 11 to 20 days per year. The days of the maximum temperature above 35 degrees Celsius will increase to 40 days per year. And the heat waves with duration larger than 6 days will increase 8 to 9 events per year. All these will have definite impact on floods and the hydrological processes. For the floods, the magnitude of maximum flow with return period 100 years is expected to decrease by about 20%, but this decrease exhibits very large spatial variation. And larger variation is expected in Northern Africa and Eastern Mediterranean. However, flash flooding is going to increase for small watersheds and decrease of the peak flows at floods is expected in large river basins. However, the population, flood-prone population exposure is going to increase, and also flood will affect larger cropland areas, and the probability for flood damage will increase. So here I'm showing a map taken by another paper published in 2011 for the Mediterranean basin, and we can see that until the end of the century, the hydrological balance will be negative by about 400 to 800 millimeters per year, and we can see this variation across the Mediterranean basin. The impacts of climate change will be on the processes. Will have reduced actual evapotranspiration, surface runoff, and groundwater recharge. The groundwater, especially the coastal groundwater level, is going to drop, allowing seawater intrusion. This will, the impacts depend on the geomorphological characteristics of the basins, and it seems small watersheds to be more vulnerable than large basins. Now, for the impacts on agriculture and agricultural water uses, the crop growing cycles are going to decrease, so we may have a rotation, more cropping during the year. The growing decrease days will increase by 40 days per year. The crop yields will increase for some, not all crops, for some crops, and we'll have higher risks and damages from the increasing severity of hydrometeorological hazards. Irrigation water requirements are going to increase, but also the monthly distribution of these water requirements is going to change. As a result, we're expecting to have larger water balance deficits, and these may create conflicts with other water uses, but also countries, because in the area we have many transboundary basins. What is the solution? The adaptation methods, for example, to change the crop pattern, improve the irrigation to save more water, use of surface water, build, as Dr. Nohara said before, he spoke about reservoirs, to build more reservoirs and to manage them accordingly, increase use of treated wastewater and saline water, and at the end we'll have build an adaptable water resources management in order, because there is continuous change, environmental, social, and climate change. So to conclude my presentation, and would like to make some comments. First of all, the uncertainty of climate change modeling should be assessed through the use of climate model ensembles, not just one model. And this uncertainty should be modeled through the impact models, for example, a hydrological or water resources management model. And the impacts on hydrometeorological hazards and water resources are very spatially variable, even in the same basin, the Mediterranean basin, as I said before, and in the globe, all the globe. Of course, we should develop adaptive management in order to mitigate the climate change impacts and find appropriate measures and actions. Thank you very much for your attention.
Thank you, Professor Loukas. So we can proceed now with the young authors and their presentations, and keeping all the questions for the end of the session.
For the end, yeah.
Okay. So you can start with the first presentation.
Are we handle the presentations?
Yes, please.
Okay.
Yes.
So let's call the first speaker. Let me see the name. It's Gediao Ayele from Australia. The title is How Much is Sufficient? Assessing Land Use Change Impacts to Improve Water Quality. Is Gebiao with us?
Unfortunately, I'm Nicholas from IT. Sorry to interrupt you. Unfortunately, Gibiao hasn't logged in yet, so we should
Okay.
continue.
Okay.
We should move to the next one. The next one is, there are many names here. Cecile Taizoun Dukan and Ayşe Mohamedoglu from Turkey. Are they
Hello.
with us? Yes?
Hello.
Hi, Cecile.
Hi,
The floor is yours.
thank you. Thank you very much. My name is Seçil Tuzundoğan. I'm working Mediterranean Fisher Research and Production Training Institute in Antalya, Turkey. The study I will present is also a part of my doctoral thesis. You can see the Aksu stream, which working area. Aim of the study is to present an integrated approach for the analysis of pressure and impact on the water quality of Aksu stream. Aksu stream discharge Mediterranean Sea, and its total length is 145 kilometers. There are Karacaoğlan 1 dam and 2 dam reservoir on Aksu stream. Pressure on water quality and quantity, intense agriculture activity in the north, and tourism activities in the south. In addition to agricultural pressure, the stream is also exposed to a treatment plant discharge as a point source of pollution. This is Kuyap Wastewater Treatment State, and Aksu 10 is my final sampling station. Monitoring study was conducted at 20 monitoring stations for a period of 1 year, and 10 monitoring stations are on Aksu stream, and 2 monitoring stations are on tributaries. As can be seen from the table, sampling could not be made at certain stations in some periods. The stream water abstract nearly all around the year for agricultural irrigation, which caused a rapid decrease in the flows and even periodic dryness, and several sections such as YQ2. Materials and methods. The monitoring study included in-situ measurement and analysis of many physicochemical and biological parameters. For example, temperature, pH, electrical conductivity, and chlorophyll A were measured in the field using handled multi-parameter instrument, name is Exosonda 2. And for analysis of bacteriological parameters, water samples were taken by filling pre-sterilized 100 milliamber glass sample bottles and analyzing. Result and discussion. As in the first graph, the annual average water temperature volumes vary between 15 and 22 degrees Celsius, but the minimum temperatures were measured in winter. And second graph is the conductivity. The conductivity remains at average volumes throughout the year. However, 10 station maximum values were also measured with the effect of the seawater. The salinity volumes appear to be parallel with conductivity. The minimum DO concentration and saturation measurement at the upstream station received the hypopolymmetric water of Karacaören 2 Dam Reservoir. Similarly, highest volume is ammonium nitrogen was obtained for upstream station. Nitrogen concentration also exhibited by spatiotemporal variation, where the yearly average volumes varied between 0.2 and 1 milligram per nitrogen per liter. And total nitrogen was measurement at similar means volume throughout the whole year. The yearly minimum and maximum concentration of BOD5 were analyzed as 1 and 11 milligram per liter at the monitoring station located very close to the incoming tributaries. The maximum yearly average concentration of COD and TOC were analyzed downstream monitoring station that received the wastewater effluent discharge. The maximum concentration of phosphate was monitored at one of the tributaries, YK1, and mean concentration volumes of phosphate were between 0.02 and 0.08 milligram per liter. The maximum yearly average concentration of TP was analyzed at the downstream monitoring station that received the wastewater treatment plant and effluents. In case of the bacteriological water quality, the maximum total fecal and E. coli numbers were obtained at downstream monitoring, whereas the maximum fecal streptococcus number of 108 CFU per 100 milliliter was analyzed at one of the tributaries that carried mostly drainage for agricultural lands. Conclusions: based on the yearly average volumes, 2 downstream monitoring stations were classified as class 3 and remaining 10 stations were classified as class 2. Water quality of Aksu stream has gradually deteriorated due to the inflows from the tributaries YK1 and 2. Deterioration bacteriological quality of Aksu stream just before its discharge into the Mediterranean Sea at first affect the recreational quality of seawater. Treatment plant effluent caused the main threat on the bacteriological quality of river and seawater, which needs to be addressed urgently. Functional cycle of the dam reservoir reduced precipitation due to the adverse impact of the climate change and abstraction of high volumes of irrigation water from Aksu stream. Here it influenced the flow regime and caused stagnant water and dry sections. There is ongoing study for the preparation of the river basin management plan to improve the water quality status of Aksu stream. Thank you for your attention.
Okay, thank you very much, Cecile. We are moving to the next presentation by Sophie Scott. Is Sophie with us?
Yeah, hello.
Okay, Sophie, you have the floor.
Okay, thank you. Okay, so I'm Sophie and I'm from the University of Sheffield in the UK. And my study at the moment as part of my PhD is titled Urban Floods, the Microbial Risk to Human Health. And it's funded by the Engineering and Physical Science Research Council, as well as the Natural Environmental Research Council. So the background of my project, it starts with climate change. So over the last 30 years, the frequency of extreme hydrological events has been steadily increasing as a result of climate change. So in the UK, extreme hydrological events usually means intense precipitation, so large amounts of rainfall over very short periods of time. And the drainage systems here were not designed to cope with such large influxes of water during these events. This leads to spills of the sewage system, and these occur when the capacity of the sewer is exceeded and water overflows before reaching the outlet of the release valve. So a lot of sewage systems have these release valves, so they're allowed to discharge this extra water before the sewer bursts. And when we have these leaks via pipes or outlets or gullies, like in the photos, we call those urban floods when they happen in a city or town environment. So the problem with the urban floods is that urban floodwater is a mixture of rainwater and diluted sewage. And so this contains pathogens that have potential to cause disease. So most of these pathogens are spread via the fecal-oral route, and they include things like E. coli, Cryptosporidium parvum, and Leptospira. And these can cause diseases ranging from gastrointestinal diseases and then more serious diseases like Weil's disease and infections. So in the short term, the risk of an urban flood is the exposure to pathogens via direct contact with surface floodwater, so potentially people walking through the flood area. But what we're more interested in is the long-term effects of these urban floods, so the exposure to the pathogens via contaminated soils or surfaces after the flood. So once the flood has arrived in an area and then moved away, does it leave any pathogens behind? And if it does, how long after a flood do these pathogens pose a risk to public health? So my experimental plan is a mixture of lab and field-based work because there are many factors to investigate to determine the risk of these urban floods. So I'm looking at the behaviour and survival of different pathogens, the transport and sorption of the pathogens in different soil types that you would typically find in a city or a town, and the movement of the pathogens between the floodwater and the soil profile. So this is a kind of overview of my experiments. So we have a column that I've designed. It's an acrylic column. It's approximately 2.5 meters tall. And the idea with this is to fill it with different soil types and run diluted sewage that replicates urban floodwater through the column, and over different time periods take samples of soil and water via sample ports and analyse those for physiochemical factors like pH, grain structure, temperature, moisture content, but also to do DNA testing to determine the species, how far down the column they travel, how long they survive, and factors like that. So that's the lab-based part of my project. My field sampling is taking place in Sheffield, which you can see here on the map in the UK. Sheffield is a historically industrial town, and it's become quite urbanised more so recently. It's got a very dense population, and there's a lot of floods that happen year on year, surface floods. So I have 2 sites in Sheffield that I'm going to sample soil and water from, and these sites are known to flood regularly. And I'm going to take these samples approximately every 3 weeks over 1 year to account for seasonal variation. And the 2 sites contrast each other quite well, but I'll go into more detail in a second about that. And another interesting part of my project is we're hoping to use this annular flume that we have at the Sheffield Water Centre. And this would just allow me to perform experiments in a lab setting, but with like mobile water rather than just water that's just sitting in one place. So with these are the different analysis that I'm going to do on my soil and water samples that I collect from my lab and my field work. So moisture, soil structure, pH, organic matter content, they're all just the basic factors that could affect the survival and behaviour of the bacteria. basic spread plates just to get an idea of the level of contamination. And then I'm also going to be using DNA analysis and sequencing, as well as flow cytometry to determine the survival rates and the species of the pathogens that I collect in my samples. So this is just a little overview of the flow cytometer. So it's usually used in medical settings to look at body cells and blood cells. And it's a machine that funnels cells one at a time through a laser. So it has the ability to count cells as well as determine the survival rates when you use fluorescent stains with them. So it uses a system of gates, which you can see on the graph, and you set these up with a known control. So I use E. coli, I use a known concentration. And so working on the control that I know that now when I run my samples through this, if any of the little dots fall in this gate here, I know that the sample that I have run, they are live E. coli cells. They fall in this gate, they're dead E. coli cells. And I also have control set up for other coliform bacteria that you find in wastewater samples. So this can't tell me the exact species, but it can tell me the amount that are live and the amount that are dead in my samples. So when that's used along with DNA analysis, this is where I get to find out the species and the source of the pathogens that I find in my samples. So I've extracted my DNA from the water and soil, I purify the DNA, and then it's ready to be analysed using next generation sequencing. So I'm going to be sequencing the 16S rRNA gene, which will allow the species of the pathogen to be determined. It will also show me the source, as in, is this bacteria commonly found in humans or is it commonly found in animals? Because then it allows me to see if the pollution in this urban flood is directly from sewage, so a human-based bacteria, or is it potentially just from rainfall and runoff, so perhaps from bird feces or dog feces, that kind of thing. So far, there has been some delays in my project due to COVID, but I have began my field sampling work. So I track the rainfall along with my samples because the nature of my work, although it rains a lot here in the UK, having the opportunity to sample when there's an actual flood is quite hard to determine when that's going to be. So I sample on dry days and I also sample on wet days just to wait around and see if there's going to be a flood. So my two different field sites are both in Sheffield. They're both near residential areas. And one site is believed to be near a CSO that's been misconnected to residential home pipes. So we're potentially getting people's dirty water coming out of the CSO. And then another site is near a children's playground, and the flood there derives from a gully that is blocked and is broken and it spills over. So at the moment, we haven't seen a difference in survival or numbers of the bacteria between dry and wet days, but we have seen that there is a lot higher numbers of bacteria found in the water samples compared to the soil, which suggests at the moment that perhaps there's not that much of the pathogens actually moving into the soil, but I have only done around 4 or 5 field site visits, and to really make any conclusions and anything to be statistically significant, I do need to collect a lot more data. So further work, I'm going to commence trials using the acrylic soil column. I'm going to carry on my regular field visits for another 9 months, and then hopefully as well perform tests on the annular flume if I have time. I have a lot of extracted DNA that I need to sequence, and then I'm going to assimilate the results and draw conclusions. And the main goal of the project is hopefully at the end, I'll have a data set that I can then use to advise the local council and government that if there is a surface flood in an area, then they can advise the public how long after that flood they should avoid the area, if there is a potential risk of pathogens being present still in the surfaces in the soil. And then hopefully it could help stop the disease there from spreading. So thank you very much for your attention. That was just a quick overview of my project. Yeah, thank you very much.
Thank you very much, Sophie. Let's move to the next presentation by Arga Pribadi from Indonesia. Is Arga with us?
Yes,
Yeah.
we are
Okay,
here.
hi, you have the floor.
Yeah, my colleagues will start first. Okay.
Okay, thank you, Arga. Okay, good afternoon and good evening. Before I start the presentation, I want to point out that this presentation will be presented by me, Gaspar Songko, and my colleague, Arka Irmawan. Both of us are affiliated with Department of Politics and Government, Gadjah Mada University in Indonesia. And next presentation, please. Well, in our today presentation, we want to discuss about the interaction between science and the policy process, and also how university as institutions who are produce knowledge communicate their knowledge in the context of water policy, especially in the water-related disaster. And to start our presentation, I would like to explain why we choose this research theme. And the first thing is we see that so far, water-related disaster projects and water policy have mostly talked about technical issues and the infrastructure dimensions such as water pipe management, water technology, and so on. But we also believe that the success of a policy and water management is also influenced by the collaboration between science and the practice of policymaking process. And this nation also based on our knowledge that many research related to water projects tend to analyze on the level of contested knowledge between scientific and indigenous knowledge. And this study tried to find boundary object in science and policy interaction. And also several studies tend to focus on the role of organization, which act as an intermediate agency to solve the boundaries between science and the policy. And based on this, we note that there is a gap on the study. So we found that there are still a few who scrutinize how the interaction and collaboration between two parties, which is the university, and how about institutions that produce the knowledge communicate this to the policymakers. Then to next slide, we want to give you some context. And on the left hand, you can see that the map represents the location where the project is conducted. It's located in the Semarang city. It's located in the coastal area of Central Java in Indonesia. And during the pandemic, Semarang city has a record as one of the cities that has a fairly high number of cases of COVID-19 infection. And then this place is also vulnerable in terms of the effects of climate change and the water-related disasters. And also on the left hand, you can see the picture show that a woman resident, which is in the WAS project, walking in a narrow road. You see that she's using a boot and also full of health protocol because she used a mask and also face protector. It's indicated that it's prevent her from COVID-19. And this picture also is a proof that the village, as the object of the research, experienced a tidal flooding, and around 3 or 4 times in a week. And of course, this process has implication for residents in this area in accessing a clean water, sanitation, hygiene, especially for the women health and also on their reproduction. And also we want to give a context that what is a WAS project. So basically WAS project is a collaborative research project between University of Gadjah Mada in Indonesia and the Monash University in Australia. And it project goals to understand the measure of local government in utilizing water and sanitation during the COVID-19 pandemic. And its aim is to promote policy with WAS knowledge into policymakers. And this project also examines to what extent women access gender-based roles, who are often seen as vulnerable groups, to assess WAS in the midst of COVID-19 pandemic. Therefore, this project also has this inline paradigm with the WAS Sustainable Development Goals in SDG framework. And we have to give you some context that this project is a fairly short duration. So it's around 4 until 5 months in 2020. Next slide, please. Okay, so this is our research question. So basically, we have 2 research questions. The first is, then we want to know about how do members of the WAS project negotiate science and policy boundaries with water stakeholders in Semarang City, and how do how do members of the WASP projects and water stakeholders in Semarang City manage the common ground about the water hygiene. And to answer this question, we use a qualitative method, especially in the context of historiography approach. And our data is based on the document that related to the WASP project that was conducted from September to December in 2020. And some of them are call for papers under research agreement, and also transcript interview by the researchers, and also the note from the focus group discussion from researcher and also from the stakeholder in water policies. And the next slide will be presented by my colleague Arga. Please, Arga.
Yeah, thank you, Dias. Maybe at first I will state that we are from the political scientists, so the analysis is maybe a little bit different with the others. And my background is when I do the master degree is in science and technology studies, so the interaction between the science, technologies, and the society. So the one of well known as concept in STS or in science and technology studies is boundary work. We use a framework called boundary work. So the boundary work is assumed that policy makers have been struggling in two ways. First, how to use the expert knowledge from the science, such as making expertise knowledge as the basis of the policy. The secondly is how to organize a working division of labor between the expert and policy makers. This difficulty is caused by the basis of our understanding so far that science or policy are completely separated. So when back to in 83 that Thomas F. Juren tell that science and policy is completely separated by ideology. So ideology from the science not to distribute the knowledge to the society is making the boundaries between them. But Hoffman, scholars from the Netherlands, offer something different. Hoffman reveals that science and policy are not completely restricted or completely different in different words, but science and policy able to coordinate and build boundaries through the three medium: text, object, and people or person. As the Hoffmans say, is called TOP model, TOP model. The text describes the language used or implied in the documents, and the object is something that is understood differently by the two actors, so that it has implication for different activities between them. However, they still refer to the object as the basis of their activity. A person describes an actor who can operate across the boundaries in science and policy, or we know as the knowledge broker or gatekeeper. With this framework, we want to try to reconstruct the negotiation and creation of division of labors between the social network practice in the WASP project, which aims to make a policy on water disaster and the climate crisis, considering that the basis of making boundaries in social process. So our analysis on using the TOP models leads to the argument that research collaboration is not entirely successful. Furthermore, the interaction between the science represented through the university, like my colleagues mentioned, and the policy, water stakeholder as well as local government does not work. Let's start with the medium text. In the WASP project, the medium text is represented on small rapid research grant document. This document is collaborative documents created by the Partnership for Australia Indonesia Research, or well known as PAIR, and the Australia Indonesia Center, or well known as AIC. The existence of this document creates a boundary between science and policy, because in the documents there are specific requirements such as a list of university of collaboration and the subtopics. The language contained in this document leads to the limitation of the policy space for future involvement in the WASP project. But on the other hand, the use of this text medium leads to knowledge collaboration between the North, Monash University in Australia, and South University of Gadjah Mada in Indonesia, which is realized based on the exchanging materials objects such as network. We identify that module object through the collaboration document, namely Small Rapid Response Grant 2. The document contains the research timeline, which is the coordination between the science and policy. The university will refer to the document as a determination of their activities, while the stakeholders will refer to the documents to see the expectation what time they will receive the research finding documents for the policy process. With the determination of the timeline, what the university and stakeholders will act according to what has been written in the document. However, in the third medium, we do not find boundary person or someone who can move across the boundaries between the science and policy. This is because of the medium of test in the Smart Rapid Research Grant documents is contribute to the demarcation between the science and policy. This is proven because in the terms of collaboration research, there is no written obligation to cooperate with the representative of water stakeholders. Water stakeholders as policymakers are seen as the ultimate goal, but there is no desire to involve them from the beginning. So based on the top model analysis, we argue that the collaboration was not completely successful. WAS project failed to manage a common ground of knowledge about water hygiene. This is due to the missing role of boundary person. Its impact on the failure of science and policy communication or interaction to create a new values and knowledge that is used as the basis for policies. In this case, water disaster and climate crisis not able to be risen because there is no common ground of knowledge between science and policy in WAS project. Therefore, the absence of boundary person makes the interaction of science and policy failure. And this is our reference, and thank you for your interest. We are open to discussion.
Okay, thank you very much, Edgar and Diaz, for your nice presentation. So let's move to next speaker. The next speaker is Vilma Gabriela Carves from Brazil.
I'm just gonna share my presentation.
Yes, sure.
It's okay, the presentation?
Yeah, we can see your presentation, but not in presentation mode.
No. And what about now?
Can you make it slideshow mode?
Yeah, it's in the presentation mode for me.
Oh, okay.
But it's not the presentation mode.
It's not presentation mode we are seeing.
Let me just...
Sorry to interrupt you again. You should click on the down right side, the book view.
Yeah, I click it. For me, it's in the presentation mode. I don't know why.
No, not the presentation view. It has another button which looks like a book. Perfect.
Yeah.
It's good?
Yeah, we could see it once.
But it's okay now, right?
You closed it again.
Yeah.
That's
yes. Now
perfect.
it's okay.
Good. Sorry. So my name is Lum. I'm from Brazil. I'm a civil engineer. I'm going to present a research entitled The Impact of Studies Implementation in the Water Metabolism of an Urban Catchment. So this research was a result from two research projects carried out in the Universidade Federal de Campina Grande, here in Campina Grande, Brazil. So in order to design and assess the performance of sustainable urban drainage systems, we must consider changes in the hydrological regime and the contributions that these studies can make in the water supply system. And these elements composes which we call the urban water metabolism. So the urban water metabolism considers input, output, and retaining water flow. And as we know, the growing surface impervious and the centralization of water supply systems are one of the causes that make urban catchment metabolically inefficient, and such can enhance the efficiency of the urban water metabolism by replicating the capacity of recycling and adaptation of nature systems. So for example, when you have a highly impermeabilized urban area, we generate large volumes of runoff, we reduce infiltration, we generate large volumes of wastewater. But when we implement studies, we reduce the runoff rates, we increase the infiltration and evapotranspiration rates, for example, and we get closer to the nature water metabolism. So the objective of our study is to quantify indicators of the water metabolism in a small catchment in Brazil for an extreme event, considering the implementation of studies. So our catchment is composed mostly of residential lots and with scarce public equipment and open spaces that are unevenly distributed throughout the catchment. And we analyzed it in our simulations one extreme event that occurred in the city in the year 2020 and generated these flooding events that we can see here in these videos. And we have to highlight that the results for just one single extreme event does not represent the catchment metabolism as long term, but with this study we aim to demonstrate how the catchment metabolizes the collective rainfall during the event that we analyze it. So in order to assess the impact of studies implementation in the urban water metabolism, we simulated 3 scenarios. The first one was the baseline scenario, which represents the current catchment conditions without any studies intervention. The scenario one, in the scenario 1, we implemented 3 studies infiltrations, which were permeable pavements, infiltration drains, bioretention systems, and in scenario 2, we added not only the infiltration studies but also the rainwater harvest systems. And these studies were placed according to the availability of urban and physical components throughout the catchment. In order to calculate the urban water flow, we used the stormwater management model, the SWIM model, and the urban water flows that we calculated were flooding volume, flooding hotspots, total runoff, peak flow in the catchment hectare, and rainwater harvest volume. And we observed that studies indeed can reduce the traditional flooding indicators, such as the peak flow and flooding volume. So as you can see here in this table, the scenario 1 and 2 reduced more than 60% of the peak flow and flooding volume if we compare it to the baseline scenario. Also, the total runoff is reduced. So in scenario 1, with the addition of infiltration studies, we reduced 65% of the total runoff throughout the catchment, while in scenario 2, we reduced more than 80% of the total runoff throughout the catchment. And with this reduction of total runoff, we aument the infiltration and the evapotranspiration rate. We alleviate high temperature and heat. And this reduced runoff also causes less impact on flooding in areas downstream the catchment. Also, we observed a reduction of flooding hotspots throughout the catchment, and this this can reveal how everyday activities can be less impacted if studies are implemented throughout the catchment. Also, when we implemented rainwater harvest systems, we not only had a reduction in the flooding and runoff, but also we helped to decentralize the conventional water supply system. Once we can make the catchment more decentralized regarding the water supply systems. And although we simulated only 200-liter tanks throughout the catchment, because we assumed that these smaller tanks would be more easily appropriated by the local inhabitants, we could try to implement bigger tanks in order to reduce even more the dependability of the basin to the centralized water supply source. So that's it. Thank you very much for your attention.
Okay, thank you very much, Luma, for your great presentation. So we are moving to next presentation. The speaker of the next presentation is Paweł Jarosowicz.
Yes, hello. Thank you very much. Hello.
Yeah, the floor is yours.
Thank you very much. I will share my screen. So it's Paweł Jarosiewicz. I know the pronunciation is very difficult, my name. Very sorry for that. Okay, I'm starting sharing my screen. Please, could you confirm?
Yes. Please go to the slideshow mode.
Yes, now it's full screen, yes?
Yes.
Yes, thank you very much. Okay, so hello everybody. Good morning, good afternoon, and good evening to all of you. The topic of my presentation is the story, how we can create the solutions, so-called eco-hydrological nature-based solutions, with the understanding of the catchment processes and the self-purification of river systems. Before I start, I would like to put your attention to the planetary boundaries that we have to deal. We have to find the solution for all those 9 areas that were identified first with the team of Johan Rockström, the famous Swedish ecologist, in 2009, and this year updated. So the update of this year was concerning the novel entities. So these are the chemicals that we are producing as the humanity, and they are entering the global system, including, of course, water resources. In my research, I am particularly focusing on pesticides, which are one of the components of those novel entities that, as you can see, we already crossed the safe zone of our planet with those pollutants. On the other hand, I am very interested with phosphorus, which is also with this biogeochemical cycle of phosphorus was, of course, altered by humanity to the large extent. So what about those two? First, the pesticides, despite our knowledge about their toxicity, the impact not only for human beings, but also for animals, plants, bacteria, still our model of agriculture and food production requires application of huge amounts of pesticides in the global scale. So this is the pollution that is continuously present in the environment. On the other hand, the phosphorus, which is so-called limited factor for eutrophisation, so another problem of degradation of water resources, is also applied with the modern agriculture systems. So as we see, this huge challenge of solving the agriculture pollution is still in front of us, particularly because it is difficult to apply such great solutions like wastewater treatment plants that can help us with point sources pollution to the diffuse scale, which will be economically impossible. So here we have another solution that we can use. This is called, you can call it nature-based solutions, but for me, the origins starting with eco-hydrology. Ecohydrology started in 1997 under UNESCO Intergovernmental Hydrological Program, and from that time it is continuously one of the priorities of UNESCO IHP. In the phase 8 that we finished last year, it was one of the 6 priorities. In the current 9th phase, it is also one of the major factors of achieving sustainable future and helping to solve the problems of water resources. So how to implement those nature-based solutions with ecohydrology? This is a very nice approach that I believe you will also find interesting. Ecohydrology is proposing this 3 steps methodology. So the first step, very important, is the quantification of hydrological cycle and pollutant sources, so-called hot moments, hot spots in the catchment size. Then we need to analyze the self-purification potential of the catchment to find the places, find the spots where the metabolism of the catchment is in the best shape, or where we can help it with our technologies. In the end, following those 2 steps, we can propose the nature-based solutions in the specific areas. So my study, as the colleagues that were speaking before of me, is the part of the PhD dissertation. We selected 4 catchments in the area of central Poland, and we found those catchments very interesting. As you remember, we were looking for pesticides and phosphorus because following the articles about those pollutants, we can find a correlation with the orchards. So for instance, the apple production, which is using a lot of pesticides. As you can see with this color marked here, you can see the biggest change of the share of the catchment use, as catchments number 1 and 2 are dominated with the orchards, over 60% of the surface. Catchment number 3, it's 20%, and number 4, it's below 1%. So we have a very nice gradient to compare the pollutant dynamics in those catchments, find the self-purification processes, and continue with our solutions. So basically the results, part of them, are that we found 30 pesticides, 30 different pesticides in those catchments. Interesting fact is that in our monitoring system, we do not find pesticides at all. The reason is because Water Framework Directive is oriented on 23 pesticides that are already banned. So we are not using them anymore, but we are still using a lot of different pesticides, and all of them are toxic. So the current methods of monitoring is not sufficient to cover the whole impact. In 82% of samples, there was at least 1 pesticide. We found many different types of pesticides. The highest concentration was over 10 micrograms per liter. And taking only catchment number 1 to count, the load for 1 year is above 5 kilograms of pure pesticide substances. So for our first hypothesis question, we found very good correlation with the percentage of orchards in the catchment and cumulative concentration of pesticides. So it helps us to locate where we need to implement specific solutions to solve the pesticides problems. Then the case of phosphorus. So this is the table of all our 12 points and different parameters of water quality that we were researching. And if you notice, the phosphates are the problem for almost all of the points. So it's still a huge problem of the agriculture areas, agriculture catchments. And also the self-purification of phosphorus, it's limited to the biotic and abiotic factors. And if we when we look closer to our sampling campaigns and compare the data for different seasons or warm, cold months, we found that during the winter or during the cold months, when the biotic factors like plants, bacteria are slowed down by the temperature, the reduction efficiency is much lower. So it was for us the idea that we need to look for the solutions that will work also during this time of the year. And again, comparing all of those catchments, you can see these 7 and 8, these are representatives of catchment 1 and 2, dominated with orchards. We have much bigger concentration of total phosphorus and also for phosphates. So again, the problem is located there. And then we started to analyze the existing eco-hydrological nature-based solutions. So there are plenty of them. I would not go into details because of the time limitations, but I encourage you to check my recent paper about them, about boosting these solutions. So maybe you will find them interesting. The common feature, the common element of all of them is so-called permeable reactive barrier. So the phase, the material, when water is flowing through, it's receiving the self-purification process. So this is how we can treat the pollutant. So we focused on this particular element, this permeable reactive barrier, and the methods of optimization. This is how the idea of BioCare was developed. Currently, it is the patent protected under the patent law that we applied to our systems. The goal was also to reduce the weight of the barrier so it can be exchanged later, because due to the phosphorus chemistry, it can be absorbed on some material, but then it cannot be removed like a nitrogen through the denitrification process when you receive the gas form. Here, phosphorus can be only stocked in one place, and then it can be released back or removed by ourselves. So this idea was to create very light barriers with a different materials inside that can increase the efficiency. So this is the BioCare where we use the LICA, so the ceramzite as the core, the biopolymer to coat the material, and a different component. For the phosphorus, the calcite was selected as the best performing material because of the calcium ions that are very effective at precipitating and sorbing the phosphates. This material received the gold medal from the International Concours of Innovation in Paris in 2019, and we were successful at implementation because one company in Poland bought the idea and they started to implement this material in our systems. So this new type, of course, we compared to the old type of barriers. We were using in those solutions the dolomite rock. The most important parameters are that we reduce the weight of the barrier so it can be exchanged much easier, and we increase the capacity for the phosphorus absorption by 20 times. So this was the major goal. The second was the pesticides. So we also checked how this material will react to the MCPA. This is the pesticide that was most often found in our catchment number 1. So the place where we would like to implement this solution. So this MCPA was removed very nicely by the BioCare with biochar or activated carbon. Here you can see this with this black color, the BioCare modified with biochar. So by those means, we found the new type of the material for removal of pollutants specific for the local conditions. So if we take catchment number 1, understand the self-purification processes there, the cycles of the phosphorus, the presence of the pesticides, we can select the concrete material to be used in permeable reactive barriers in our nature-based solutions in future. So thank you very much for your attention. Please contact me if you have any questions, would like to collaborate, and visit my Twitter that I started recently. Thank you very much.
Hey, thank you, Paweł, for your nice presentation. So we are moving to next presentation. The speaker is Borko Radojevich from Serbia.
Yes, thank you very much. Do you hear me?
Yes.
Okay, I will start sharing my screen.
Yes, please.
Do you see my screen now?
Yes, nothing slide mode. Yes, now it's slide mode. Perfect.
Okay, thank you very much and good day to all of you. My name is Borko Radojevich and I will present the research of this paper. What is the main objective of this research is to inform the wider scientific and professional public with the scope and results of the research project assessment of climate change impacts on surface water regime in Serbia. There are several global models that are used to assess the basic elements of the hydrological cycle, temperature and precipitation in potential change conditions. For the design of the future climate state in Serbia and needs of the scientific project, a regional climate model was developed and used. The name of the model is EBU-POM, which means ETA Belgrade University Princeton Ocean Model. What is really important to mention is that all calculations were done using monthly data. In this research, we did the predictions according to the climate scenarios of the IPCC for the 4th panel and the 5th panel. And also we did a comparison with the results between them. For the IPCC 4th panel, the reference period for the climate, for the current climate was from 1961 to 1990, and the prediction for future climate assessment for near future, middle of the century, and for the end of the century. For the IPCC 5th panel, the reference period was from 1986 till 2005. And also we did for near future, middle century, and the end of the century. It is really important to say that in the 5th panel, periods of the prediction are really shorter than periods in the 4th panel. According to the IPCC 4, for the period of last 30 years of 21st century, A1B scenario is selected as average, and for the E2 scenario was selected as the most extreme. Also, according to the IPCC R5 panel, all periods are integrated with RCP 4.5 and RCP 8.5 scenarios. Also, it is important to mention that A1B can be comparable with RCP 4.5 scenario as an average, and A2 can be comparable with RCP 8.5 scenario. Study area. For the purpose of adopting the most appropriate methodology, 4 river basins are selected with long-term measurements of the main elements of water balance. We had available hydrometeorological data for the reference period. We have discharge, precipitations, and air temperatures. For the future periods, as output of the global model that I mentioned earlier, we got future precipitations and future air temperatures. And after that, we made a modified model ACRV and C, which gave us the monthly discharge in rivers for all these catchments or basins. VNC model relies on the nonlinear correlation that is used to generate a time series of mean-monthly flow rate on unstudied hydrological basins. In this presentation, I just put the final equation where the alphas are coefficient calculated using determinants of standardized correlation coefficients, while U's are calculated standardized hydrological parameters values. And for the results, there is a result for the 4th panel for the all 4 catchments, and we see that for the all scenarios, we have a decrease in discharge in all rivers. And for the 5th panel, I will show you just for the one basin because for the other basin is still in progress. We can see that also for the 5th panel, we have also decrease in the discharge. But then if you compare it with the period that we had. The difference is big. In 5th panel, we have 21.23 compared to 23 to 0.2 cubic meters per second, and for the fourth panel, we have degrees of discharge almost 2 cubic meters per second. And for the conclusion, we have, for the fourth scenario, we have that precipitation would be reduced about 12%. That's an average value, and the temperature will increase almost 4 degrees Celsius in the end of the century. For the fifth panel, the precipitation would be reduced about 20.5%, and the temperatures will increase almost 5 degrees Celsius. And all that will cause a decrease in discharge, so we will probably have issues and some problems in the future because of the climate change. Thank you for your attention.
Thank you very much, Orko, for your great presentation. So now I'd like to invite the last speaker of this session, Stephen John Fortune from Cameroon, I hear.
I think they are not here.
Okay. Okay. So, yeah, we had all presentations in this session. So actually, we are running out of the time this session. But I'd like to introduce one question which is posted to the chat box from Pavel to Sophie. Pavel, would you like to make this question again directly to Sophie?
Oh, yes, I would love to, but I am afraid Sophie is not here.
Oh, okay. Okay, yeah.
Thank you.
Okay, so because of the time limitation, so we'd like to close this session. Okay, so Professor Lucas, would you like to give some closing remarks?
Okay, I would like to thank all the new scientists and engineers who presented their work. Unfortunately, we ran out of time and we don't have time to make discussion on all the presentations. But I think the presentations were, all of them, were very interesting. And I would like again to thank the presenters.
Okay, so thank you very much for all participants, speakers, and also the organizers for this session, joining this session. So I'd like to close this session now. So we also have coffee break time from now here. So if you have any questions to speakers or to us, please remain here so that you can raise a question. So thank you very much for joining this session.
I would like also to thank two mentors of these sessions and everyone who attended the session. And we will have a 5-minute break until the next session starts. So thank you very much, all of you.
Okay, thank you.
We have a raised hand. I don't know if it's a question of Mustafa Safarov. I don't know.
Let me give him, let him allow to speak.
Okay.
Mr. Safarov.
Thank you very much, Mustafa Safarov. I just would like to ask, in next session, I have presentation, so you can check.
You will be promoted for the next session. No problem about that. We thought that you had to answer something about this session.
Okay, thank you.
Okay. Bye-bye, everyone.
Okay.
Meet you again.
Yeah.
In a few
Bye.
minutes. Okay, bye-bye.
We'll see you today. See you again.